All right, continuing on 8.1. Hope you remember these. When you have a set of particles that are locked in and you increase the temperature on them, what happens is these start to vibrate, and they're vibrating faster and faster and faster and faster. At some point, these rigid bonds cannot hold them in place. They're still attracted to each other, but the bonds cannot hold them in place. If the bonds cannot hold them in place, then these things are start to become free to move relative to each other. Not far, because they're still attracted to each other. They're still stuck together. But these bonds become more like slinkies or flexible bonds. So going from here to here, we go from solid to a liquid. And further, if you keep vibrating, these things get going too fast, and eventually they break the bonds. Stickiness is not enough to hold them in place, and they end up going whichever way they want to go with no bonds at all. No bonds at all. To do this, though, requires energy. You're taking something that has rigid bonds locked in place. You have to add enough energy to cause these bonds to be broken sufficiently so that it's just the stickiness holds it together. And further, when you go from this set to this set, you need to actually break the bonds. Those require energy. We call the energy necessary to turn 1 kilogram this way, we call it the heat of fusion. And we call this the heat of vaporization. We don't call it that, we call it vaporization. So heat of vaporization. So the formula for how much heat it takes to heat something up is fairly simple. It's just going to be the heat necessary is equal to the mass of the sample you're trying to melt, in this case, heat of fusion. And then if you want to vaporize it, it would be the mass times the heat of vaporization. Again, those are also on your formula sheet that I've given you. Okay? So with that in mind, try to do number 5. I'll pause this right now, give you how much time it takes to do it, and then start this video up again, and we'll do 5 together, and then we're going to have to do 6 together. So if you want to start 6, you can. All right, a 40-gram sample of chloroform is condensed from a vapor into 61.6 degrees Celsius to a liquid at 61.6 degrees Celsius. Well, the first thing we need to consider is whether or not that's at the boiling point. If it's been condensed at that point, it probably is the boiling point. So we can move forward from there, something we'll run into later. My apologies. Move forward. We have a 40-gram sample of chloroform. Okay. 61.6 degrees Celsius, and we're going to turn it into 61.6 degrees Celsius. So there's no change in temperature. So the only thing that's changing is we are condensing it. Okay? So the amount of heat necessary to condense something is the amount of heat it would take to heat it up. In other words, that's how much you get out as opposed to putting in. And that would just be mass times heat of vaporization. They tell us that we get 9,870 joules for 0.040 kilograms times heat of vaporization, which is what we're looking for. So quick calculation, I get the heat of vaporization, and these numbers are going to be large. It takes a lot of energy to break these bonds. It's going to be 247,000 joules per kilogram. Fair enough? All right, everybody try number 6. You're going to get this wrong. Use a pencil. Use scratch paper if you need to, but you're going to have some trouble with this. Go ahead and try it. Start this back up when everybody's done. All right, here we go. Let's see if I can fit it all on a smart board. All right, I've got ice sitting at negative 30 degrees Celsius. When I add heat to it, it doesn't melt. This is the part people have real trouble with, okay? Unless I concentrate an awful lot of heat in one spot, some of it might melt. But if I generally spread the heat around, all that happens is the particles start moving faster. Since they can move faster and stay a solid, that's where the energy goes. And so we would start off by saying the amount of heat first would be used to change the temperature of the ice. But then something happens. I get to 0 degrees and I can't shake anymore without increasing without breaking those bonds and starting to make them flexible. Okay, so in order to do that, I'm going to have to melt it. Now, while melting, the temperature stays the same, as long as the heat's evenly distributed. After I melt it, then I'm going to have to change the temperature again. I got 0 degree water. It's not going to turn to steam there, so I have to change the temperature of the water. Now notice the specific heat for this and the specific heat for this are different. Okay, they're not the same. Next thing up would be to, once I get it to 100 degrees though, so I'm going from 0 degrees to 100 degrees here. Otherwise, going from negative 30 degrees to 0 degrees here. Once I get to 100 degrees, now I can't continue increasing the speed of the particles without breaking the bonds. To break the bonds, I'm going to boil it, or evaporate it, or vaporize it. And then I'm going to change the temperature because I'm at 100 degrees when I'm done with this, because I haven't changed temperature at all. And so then I'm going to do delta T of the steam. Now, it could be argued, how can you perfectly do this? As it turns out, it doesn't matter. Okay, this is the way we think about it, but if you heat one in and then heat the other in later, you could actually do this as 2 separate problems, by half an ice cube, you get the same answer. So it doesn't matter which way you distribute the heat, but this is the way to think about it that yields you the best answer with the least number of steps. And it's not going to feel like the least number of steps as is. So the changing temperature formula is MC, T minus T naught. The melting temperature is M heat of fusion. The heating up of water formula is MC, T minus T naught. My boiling water is M heat of vaporization. And my change in temperature for steam, again, MC, T minus T naught. Starting over again, I have a mass of 1. Specific heat for ice I have to look up separately because that's a different number. And so I would look it up and I would discover it is 2060. Notice it's a much bigger number than the metals we dealt with earlier. Water takes a huge amount of heat to make any changes at all. Final temperature is 0 minus the initial temperature of 30 degrees plus, now I got the next mass, which is also still 1 because I hopefully didn't lose any mass. Heat of fusion for it, we look it up. Heat of fusion's on the same chart. Find it out there. It should be in the middle. There it is. I got 3.34 times 10 to the 5th. Note, it says down below melting MP is 0.000. That is the melting point, right? So if you didn't know what the melting point of ice is, you could look it up on the table. Moving forward, I've got mass, which is 1 specific heat of water, which is 4180. Final temperature is 100, because that's where it has to stop being water, minus the initial temperature, which is 0, plus the mass, which is 1 again. Now I'm on heat of vaporization. Heat of vaporization, I look it up on the chart. It says that it's 2.26 times 10 to the 6th. Please note, also the boiling point is listed there. And then mass, specific heat of steam, find steam, 2020. And then final temperature minus initial temperature, which is going to be 120 minus 100. Sorry, I ran out of space. Told you I was gonna though. All right. So slap that all into your calculator. See what you get. 1 times. Notice how the heat of vaporization is a huge part of the heat. Hopefully I got the same answer. I did, so I'm feeling really good about it. 3.11 times 10 to the 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 6 joules. And if you think about it, this represents 2/3 of it right there. Fair enough? All right. Please get assignment 8.5 and have at. You should have it already.